Hello, I'm Pete Wolf. Welcome to the media module titled Targeting Large Hail and Damaging Wind. You're strongly encouraged to complete the Targeting Small-Scale Temporal and Spatial Threat Areas module before completing this one. The Targeting Large Hail and Damaging Wind module essentially serves as an addendum to that module. This module will focus on how the mesoanalyst can help recognize favorable or unfavorable environments for large hail or damaging winds to support targeted threat messaging from IDSS and warning staff. More detailed information on forecasting hail and wind can be found in WAC modules within the CLC. However, there is some advanced level information within this module that may not be found in the CLC. Here are the objectives for this module. We'll start by reviewing the key ingredients for the formation of large hail, and then try to understand the key data fields for assessing large hail potential. Then we'll turn to damaging winds and focus on the key ingredients for that, and understand the key data fields for assessing the potential for damaging winds. Then we'll turn to how the mesoanalyst can monitor small-scale environment changes in time and space that can either enhance or minimize the threat for large hail or damaging winds. The key ingredients for large hail are fairly straightforward. You cannot get large hail at the ground without them. They include a tall enough updraft to support large hail. You need hail embryos, not simply supercooled water. You need an intense enough updraft to support hail growth. You need enough residence time for the hailstones to grow. And you need sufficient mid-level storm relative flow for particle separation based on size or weight. In essence, you want the large hail to fall to the ground away from the shaft of heavy rain. How would you answer this question? Why is the environmental freezing level not a significant factor in determining whether severe thunderstorms are favored or not favored to produce large hail? In fact, answers A through C are all correct. Perhaps contrary to popular belief in the operational forecasting world, the height of the environmental freezing level is not a significant factor. Why? Because hail doesn't develop outside of the thunderstorm. If anything, you should look at the estimated freezing level within the warmer, saturated updraft core. That would probably be more relevant. It would also be considerably higher than that within the ambient environment. Even so, the depth of the core above that level and whether the hail falls within or away from heavy rain may be more significant issues. So let's look at the key ingredients for large hail. First, we need a sufficiently deep and intense updraft to support the growth of large hailstones. We tend to look at instability and deep layer shear to assess this. CAPE that exists below the freezing level, which is shown as the blue shaded area, is generally irrelevant for hail growth potential because we're below the freezing level. It may have some role, however, in supporting a stronger updraft. In particular, though, we focus on CAPE within the hail growth zone, shown in the red shaded area, generally between the -10 Celsius and -30 Celsius levels. We also look at deep layer shear, which can enhance updraft intensity, particularly in the presence of more marginal CAPE. Next, we need hail embryos, or graupel. And for that, we need the cores to develop in the air that can support ice particles. One thing to point out with regard to the sounding: the difference between the freezing level within the updraft core and the general environment freezing level, or wet bulb zero level, can be substantial, greater in large CAPE environments than small CAPE environments. Now, hail embryos generally require temperatures colder than about -6 Celsius. Therefore, precipitation cores that form below this level are likely to grow vertically as supercooled water, potentially without the ice particles needed to support hailstone formation. Compare these three storm cells. There are 50 dBz cores that are shown. I'm also showing the wet bulb zero heights, representative of that within the updraft cores. From a hail growth perspective, can you see why core A on the left is favored to produce the largest hail, and core C to the right is likely to produce little or no hail due to lacking hail embryos and little area for growth? Next, we need longer-lived updrafts, and for that we need some separation between the updraft and developing downdraft. Otherwise, the precipitation falls through and weakens the updraft, as we tend to see with pulse storms in the summer. The hodograph can help us assess this. It shows the pattern of storm relative flow vectors and shear vectors with height, which relate to the orientation of the storm and how precipitation is spread out down shear. This allows the updraft to remain intense longer, supporting large hailstone formation, and reduces the melting impact that occur if the hailstones were to descend within a heavy rain shaft. Which now gets us to the final requirement, ensuring the hailstones don't melt before reaching the ground. What do you think is the most significant factor when it comes to hailstone melting as it descends? The answer is D. You don't want the hailstones to descend within heavy rain. You want it separated from the rain shaft. Now, I should point out that what is typically taught is answer A, along with other factors like hailstone density and atmospheric moisture content, and those could have small impacts. Their impacts, however, are much less for very large hailstones than for marginally severe stones. More significant, however, is whether hail falls within or outside of the heavy rain. A simple lab exercise can be performed to illustrate why that is correct. Back around the year 2000 in Wichita, Kansas, I completed a simple lab exercise along with a lead forecaster focused on the melting of ice cubes. We used 3 sizes of molded ice cubes in the experiment. Molds were used which created halves of the sizes that are shown here. We ran 2 runs of this experiment, one that was indoors using a temperature of 73 degrees Fahrenheit. This would be similar to a summertime air mass with surface temperatures around 95 degrees, temperatures at 500 millibars just below freezing, and high wet bulb zero heights above 12,000 feet. Then we did run outdoors with a temperature of 85 degrees. That's 85 through the entire melting layer. That would be similar to a much more extreme air mass with surface temperatures around 110 degrees Fahrenheit and 500 millibar temperatures way above freezing, which we don't even observe, along with very high wet bulb zero heights. So we took the ice cube halves and placed them on a screen well above the ground or floor to allow melting water to shed from the cubes. And we took diameter measurements every 2 minutes along with digital photographs. And we compared the different runs. So let's look at what the results were. So here was the original state at 0 minutes. You see the 3 ice cubes here in different shapes. We're really going to focus here on the middle one, which was about just a little larger than ping pong ball size. So here we compare the 2 runs, just having them sit outside or indoors with nothing going on, no water, no wind or anything, just sitting there to see if they would melt. And you see with the indoor temperature run, which represents a very warm environment, summertime, there was very little melting, even after 4 minutes, about the point when the hailstone will reach the ground. Very little melting at all. When we put them outside in an extreme environment that we rarely ever see with severe storms, we do see some melting, particularly the smallest ice cube, but mostly wetting of the larger cubes. Then we looked at a different comparison. We did 3 runs, one in a dry, warm environment like we just showed in the last slide, and then a second run in kind of a moist environment where we occasionally sprayed water just to try to create moistness where the ice cubes were located. And then a third run where we continuously sprayed the cubes with water. So try to simulate numerous continuous collisions with raindrops during descent. Here we see a substantial difference. You see the initial run on the left with warm air, summertime environment showing no melting. If you look at the far right, in a simulation of hailstones falling through heavy rain, what a difference. The ping pong ball size storm is gone in 4 minutes before it would reach the ground. Even the largest one showed substantial mass reduction. This was a rather shocking finding for us. We thought there would be some increase in melting, but to that extent, I think was unexpected. The conclusion from that lab experiment was that melting in general is not a major factor in hailstone size at the surface, except when hail falls within the heavy rain shaft. And in observations, typically when you have heavy rain, when hail occurs with it, it tends to be pea-sized or small marble size. Rarely, if ever, do you see golf ball or baseball sized hailstones amidst a heavy rain shaft. Usually those kind of stones fall separately. So the experiment suggests that we need ingredients aloft, particularly storm relative flow or mid-level shear, to cause the downdraft, the area of heavy rain, to be separate from where the larger targets, the hailstones, would fall. A separation of particles based on size or weight, allowing hail to fall separately, minimizing melting potential. From all this, it should be no surprise that supercells associated with longer hodographs represent the favored convective mode for large hail, especially golf ball size or larger. Whereas a short hodograph, as we might see in summertime pulse storm environments, would support hailstones descending within heavy rain, the greater shear profiles associated with longer hodographs support separation of smaller targets, that is raindrops, from the larger targets or hailstones. Environments favorable for very large hail tend to occur most frequently across the central United States, where we more often see the combination of high instability resulting from very steep lapse rates near the surface and aloft, and longer hodographs that support particle separation. Take a look at this question. Radar imagery, as shown to the right, shows a potential severe storm. It suggests large hail exists within the storm. The mesh from the hail algorithm suggests potential for ping pong ball sized hailstones, and dual pole data also suggests large hail aloft. The storm tracks slowly over a populated area and collapses. Only heavy rain and pea-sized hail are reported, no severe hail. What are possible reasons why this was the result? The most likely reason would be answer A, that large hail that likely existed in the storm, as demonstrated by a dual pole radar, descended within a shaft of heavy rain, with continuous collisions with raindrops supporting rapid melting of the hailstones, with only pea-sized hail reaching the ground. Note how vertical the core is in the cross-section. Answer C would also be possible if sufficient particle separation existed, as the smaller hailstones would likely melt if they fell within a heavy rain shaft. Let's focus now on the mesoanalyst's role in monitoring for the potential of large hail, which includes monitoring for environment changes that can support large hailstone development, and monitoring storm structure and storm motion changes, and thus changes in storm relative vectors, promoting particle separation that can influence hail melting, either to enhance or minimize. There are several potentially useful fields one can look at to evaluate large hail potential. Some examples. Here we see CAPE in the hail growth zone, generally the -10 Celsius to -30 Celsius layer. Particularly values of 7 or 800 or greater favor very large hail, golf ball size or larger. In the example shown on the right, we're really focused on west central South Dakota and possibly southeastern North Dakota. Large mid-level lapse rates, greater than 6.5 or 7 degrees Celsius per kilometer, are also quite favorable. In this example, we see widespread areas of 7 Celsius or greater across the Dakotas. We also want deep layer shear, which we also see here across the Dakotas as being favorable. You also look for lifting mechanisms to support convective initiation, of course. In this particular case example, that was focused over the central and western parts of South Dakota, where we had severe storms develop that produced very large hail, along with damaging winds. Take a look at this sounding and hodograph. Would you anticipate a significant supercell here? There is decent instability, but deep layer shear is pretty marginal. However, what if mid-level flow was about 10 knots stronger to the south of the sounding site, and there were indications of enhanced easterly inflow into the developing convection, such that you get a hodograph shape more like the purple example? These small-scale changes can increase vertical shear to a level more supercell friendly, and as you see, the anticyclonic curvature is a bit more enhanced. What do you think that would support? On this particular evening, a lone supercell developed in north-central Florida, a dominant left mover with impressive vertical structure supporting at least ping-pong ball-size hail. While the pre-storm environment may be less favorable for this result, the mesoanalyst needs to monitor small-scale environment changes that could lead to this surprise, which was the only significant thunderstorm to develop across the northern half of Florida that evening. Okay, let's turn to the damaging wind threat. First, what do you think is the key factor that drives the winds within and surrounding a thunderstorm? The correct answer is C, pressure perturbations within and around the storm. Why? Because changes in pressure in time and space drive the wind. The other factors have a lesser level of relevance. So the correct answer is as valid for pulse severe storm downbursts in weak flow environments as for derechos producing widespread damaging winds in high shear environments. While the strength of winds above the ground can be a factor, it is likely one that is aided by vertical perturbation pressure gradients that drive the wind, rather than something being mixed down to the surface. And that is because we'd have many more widespread damaging winds with squall lines if focus was just on mixing down stronger winds from above. Here is an example of a narrow squall line moving across the northern half of Georgia, producing very little in the way of wind reports. The sounding right at the time, just ahead of the line, was fairly favorable, showing no low level of inversion, some cape, and strong shear with 55 to 60 knots at 850 millibars. You see on the lower right image the low-level jet right over the northern half of Georgia. Yet no damaging winds were reported, likely due to the lack of the perturbation pressure gradients needed, which may have actually developed as the line moved into South Carolina and started producing damaging winds. The key ingredients for damaging winds include instability and deep layer shear as we look at it for large hail. But our focus here is more on generating sufficient pressure perturbations to support damaging winds. To start with, we look for large cape down low in the lower half of the sounding. Where cape is lacking, then we would want more extreme low-level shear. We want conditions that favor an intense updraft down low. This leads to perturbation low pressure near the surface. Then we look aloft for large cape or stronger shear that supports a buildup of a large core of precipitation in the mid-portion of the storm, leading to a perturbation high pressure aloft. This can be aided by evaporation of precipitation particles due to dry air entrainment or melting of hail embryos that support a colder, heavier core, building perturbation high pressure aloft. The evacuation of precipitation particles through an anvil, while helping maintain updraft intensity, can weaken the perturbation high. Take a look at the three hypothetical thunderstorm reflectivity cores shown below. Which core do you think reflects the strongest low-level updraft, supporting the strongest low-pressure perturbation near the surface? Generally speaking, a more intense updraft would support a more elevated core and a more intense core aloft. And that looks to be core A. The core that likely reflects the weakest is probably the lowest centroid and weaker core, which would be core C. Which core do you think reflects the strongest high pressure perturbation within the storm core? Just from what is shown here, you likely have a greater or more dense, heavier core with core A, possibly water-coated hailstones, melting hail, as reflected by the higher reflectivity values shown. So the most likely core to have the greatest high pressure perturbation aloft is likely core A, the same as with question number 1. Thus, the core that has the strongest vertical perturbation pressure gradient likely to support damaging winds would be core A. It does not necessarily relate to the tallest core. Even for a squall line with bowing segments, there are likely greater pressure perturbations along the portion of the line where the bowing segments develop, with a perturbation low just ahead of the line where air ascends into the updrafts, and a perturbation high along and following the convective line. You could even have a perturbation wake low behind that. The descending rear inflow Impinging on the line may also play a role in generating these pressure perturbations and thus damaging winds. Sometimes the wake low pressure perturbation can be strong enough to generate strong winds on the backside of an MCS. The most challenging aspect of anticipating damaging winds comes when dealing with convection that appears to be elevated over a near-surface inversion. Will you get damaging winds at the surface, or will you get 20 or 30 mile per hour winds at the surface while stratus fractus clouds a few thousand feet above the ground race across the sky at 60 miles an hour? And I've seen that multiple times. Once again, focus turns to the development of intense vertical perturbation pressure gradients within the convective cores. This can be accentuated when you have a low-level temperature profile close to pseudo-moist adiabatic, such as the left example, compared to a stronger low-level inversion on the right example. The existence of that inversion, however, does not necessarily preclude damaging winds. I've seen examples of bow echoes producing damaging winds on the north side of a warm front where temperatures and dew points are only in the 40s, yet generate damaging surface winds. The Boeing segment somehow develops the kind of intense pressure perturbations needed to develop damaging winds even down to the surface. So for individual elevated cells, the inversion may prevent damaging downdraft winds at the surface, while an intense QLCS could develop near-surface pressure perturbations to drive surface wind despite the presence of the inversion. How would you answer this question? True or false? A line segment of thunderstorms is racing eastward at 65 miles an hour. Because of its motion, one should expect damaging winds in the 60 to 70 mile per hour range. Well, as given from the last slide, just because you have something that suggests damaging winds doesn't mean it actually will occur at surface level. So this is false if the pressure perturbations don't support that level of wind at the surface. Plenty of times, rapidly moving squall lines or line segments or even discrete storms have not produced damaging surface winds, likely given the presence of a near-surface inversion. Some form of pressure perturbation is needed to drive strong winds to the surface. How about this question, true or false? In pulse storm environments, taller storms will produce stronger downdraft winds because of greater distance for the downdraft to accelerate to the ground. This also is false. Taller cores produce greater depth for precipitation to fall, but it is pressure, not precipitation, that drives the wind. A shorter, more intense core with an elevated base could support greater pressure perturbations for damaging downdraft winds than a taller but weaker core without an elevated base. So you could have a taller core, perhaps 50 dBz up to 40,000 feet, that produces less surface wind than a shorter core, maybe 50 dBz to 33,000 feet, but with a 70 dBz core and an elevated base. Now, there is likely a relationship in which taller cores also contain a greater core than more shallow cores, thus leading to stronger winds from storms with taller cores, but that may not always be the case. So how can the mesoanalyst monitor for damaging wind potential? That person can monitor the environment for conditions that would support the formation of the pressure perturbations that can drive damaging winds, looking at observed and forecast soundings and relevant SPC mesoanalysis plots, such as downdraft capes and lapse rates. A person can also monitor storm structure that could give clues to the needed pressure perturbations. Examples of these clues would be a tight leading reflectivity gradient, development of an intense elevated core aloft, acceleration of a storm or portion of a line reflecting changing propagation, the strength of mid-altitude radial convergence aloft, vertical orientation, and so forth. So let's focus on understanding the potential for very intense low-level updrafts that promote a perturbation low pressure near the surface beneath the updraft and the buildup of mass supporting perturbation high pressure in the mid-portion of the storm. What would the mesoanalyst look at in terms of near-storm environment to anticipate this pressure perturbation pattern? Well, for developing a more intense near-surface low-pressure perturbation, we would want a pattern of instability and shear that could promote intense updrafts. Either very large low-level cape, or you could have smaller cape but with more intense low-level vertical shear. Also a pattern of storm relative inflow and conditions that promote storm top venting that also could enhance updraft intensity. For developing a more intense mid-storm high pressure perturbation, we want to promote a cold heavy downdraft. which include conditions such as a steep lapse rate aloft, dry air aloft, large positive area in the middle portion of the troposphere, strong low and mid-level flow that could impinge on the backside of the storm. This would require some storm relative flow aloft. And finally, favorable conditions to promote buildup of a large precipitation core, which tends to be particularly favorable for producing intense microbursts from pulse storms. Now we're going to look at a case example from December of 2017. We'll focus on a QLCS event across northern Florida. This was on a day when a significant severe weather event was expected across Mississippi and Alabama into the Florida Panhandle, with the threat decreasing as it spread eastward to the coast during the night, given the expectation of reduced instability to support an advancing squall line. To the right is an animation of the QLCS early on across the eastern Florida Panhandle. Here we can see the 0Z Tallahassee sounding taken just ahead of the QLCS, showing decent instability and strong shear. Further east, the Jacksonville sounding showed lesser instability, which may decrease further during the evening. The models provided different solutions. Here we see on the right the 18Z NAM suggesting a surge of mid-60s surface dew points that would lead to an excess of CAPE values of 500 or greater joules per kilogram ahead of the squall line, while the 23Z RAP to the left, upon which the SPC mesoanalysis data is initially based, does not. Here are the surface maps for 0Z and 2Z. We can see a surge of 65 to 67 degrees surface dew points just ahead of the squall line, which is marked by the red dash line. This would support the NAM solution of an axis of sufficient CAPE to maintain the squall line intensity as it moved eastward. Note the somewhat more southwesterly surface flow associated with the higher dew points. Also note that overall, there is likely very little change in stability during this period. Even where temperatures are falling slightly, dew points are rising. Now the SPC mesoanalysis page, surface-based CAPE, which is based initially on the RAP, suggested some stabilization during this period, perhaps leading to a less favorable environment for the squall line as it progressed eastward into northeastern Florida, furthering the SPC outlook suggestion of a decreasing threat with eastward extent. The surface observations, however, were not suggesting this. Here's a look at the 18Z NAM forecast sounding for 0Z, showing a favorable environment to support the squall line over northwestern Florida. However, it also showed on a Jacksonville sounding that, if modified with mid-60s dew points, would also be fairly favorable without the SIN suggested by the SPC mesoanalysis output. Regardless of the level of instability, we also need to evaluate the dynamic side that could drive the squall line through even a less favorable environment. Here the SPC page shows an intense cold pool in the wake of the squall line. The coldness of the downdrafts is indicated by surface temperatures behind the line well below the dew point values ahead of the line. In addition, we see strong overlap of low-level moisture convergence and upper-level divergence associated with a strong system aloft. This steadily progressed eastward with the line. So there was considerable forcing to maintain the line, even where substantial CAPE could be lacking. Here are SPC plots of downdraft CAPE, which forecasters might examine for damaging wind potential. There is potential for this field to be misused, as it may not have a direct relationship to QLCS-induced damaging winds, so caution is needed here. Here we see a short radar animation about 90 minutes prior to the QLCS reaching the Jacksonville metro area, the largest population in the entire forecast area. Think for a moment how you might answer these questions. The first one is likely toughest. Reflectivity imagery has some clues to potential damaging winds along the line. Note the breaks in between the cells and the southeast to northwest extension of the cells. As for mesovortex development, based on the forecast sounding wind profiles, the 0 to 3 kilometer shear vector is roughly oriented southwest to northeast, at a slight angle to the line, but with values only around 30 knots. So the usual 3-ingredient approach might not be met. However, focus on the short line segments within this line that are oriented more north to south, or even north-northwest to south-southeast, more perpendicular to the shear vector, where the three-ingredient approach could be met. Based on the data shown, particularly observational data, one should anticipate that the squall line will likely be driven all the way to the coast, given strong dynamic support and at least a marginally favorable environment where mid-60s dew points exist to maintain the intense line of convection. The area of greatest threat where these conditions would be met for damaging winds would likely be along and just south of the I-10 corridor, or roughly downtown Jacksonville southward across Clay and northern St. Johns counties. In this particular area, you might provide targeted threat messaging of damaging wind and isolated tornado potential well in advance of the arrival of the QLCS, even despite the lack of wind reports with the line over interior Northeast Florida. Here is the 3Z surface map showing the mid-60s dew point surge getting to near downtown Jacksonville, with somewhat lower dew points to the north. The actual 0Z Jacksonville sounding is shown here. It is likely reflective of 3Z conditions north of the city. Modifying it for conditions within the dew point surge suggests sufficient instability and minimal sin, as the 18Z NAM forecast suggested, to maintain the squall line. Here we see 2Z forecast soundings for northwest Florida on the left, just ahead of the squall line, and the Jacksonville area on the right. This gives a decent side-by-side of likely conditions south of Jacksonville, similar to the left image, and north of Jacksonville, similar to the right image. While the right sounding doesn't necessarily negate damaging wind potential, given very intense dynamic support for the approaching QLCS, the left sounding certainly appears more supportive of surface damaging winds. Here is the 3Z pair of radar images from the Jacksonville radar. What would your expectations be across far southeast Georgia and along the Florida-Georgia border versus across the Jacksonville metro area, including Duval, Clay, and St. Johns counties? Is there any area you would target to message potential for enhanced severe weather and possibly even tornadoes? Where do you see intense segments oriented more north to south or even north-northwest to south-southeast that could support mesovortex formation? This is not necessarily an easy case, as there are potentially conflicting signals. On one hand, it appears conditions are favorable for damaging winds with the squall line, especially any Boeing line segments or mesovortices. On the other hand, radar is not showing much wind on the velocity images with the squall line as it approaches the Jacksonville metro area, and there haven't been any damage reports yet further west. No watch is in effect for northeast Florida. Acting only based on radar, you might just go with statements, suggesting the potential for 45 to 55 mile per hour winds along the line, with possible minor wind damage. This represents the actual decisions made for the Jacksonville metro area. However, if you incorporate environment into the process, it may lead you to continue severe thunderstorm warnings, at least for the Florida portion of the line, with conditions perhaps less favorable further north. You may even monitor for possible tornado warnings, or include tornado tags if needed if you see mesovortices develop. This was likely the decision that was needed, as you'll see. So what happened? We had a swath of damaging winds across northern Florida, with a few tornadoes reported in far northeast Florida associated with a QLCS mesovortex. Only isolated wind reports occurred in southeast Georgia. There were wind damage reports over interior areas, but they lagged real time, so they were of no use during the actual event. The lack of real-time reports does not necessarily mean no damage is occurring. Radar didn't show damaging winds in the velocity imagery due to the fact that the strong low-level flow was oriented nearly perpendicular to the JAX radar beam as the line moved over the JAX metro area. Now further to the west, the beam was likely overshooting the lower level damaging winds. In this case example, can you see how the mesoanalyst can not only help with warning decisions, but also help with targeted threat messaging well in advance of the threat? Here is the radar animation of the event, with reports overlaid on the last image. A significant swath of wind damage, along with brief tornadoes, were associated with a mesovortex that formed and tracked eastward across northern Clay and St. Johns counties. Notice that the velocity images did not pick up the damaging winds until it was approaching the coast, but it did show the mesovortex fairly well. Can you see how the mesoanalyst can help produce better results rather than simply relying on radar, which in this case did not clearly show the threat, at least on velocity imagery? So in summary, with knowledge of the key ingredients that support large hail and damaging winds, the mesoanalyst can monitor for small-scale environment changes that support or oppose such hazards. The mesoanalyst has a variety of data available to complete the task. The case example presented here was a simplified version of the task. In reality, the mesoanalyst needs to ensure the data accessed are accurate and that correct conceptual models are used. The mesoanalyst can also be helpful in highlighting potential technological issues, such as that shown in the case example, that can negatively impact severe weather operations. And the mesoanalyst can be helpful not just in supporting better warning decisions sooner, but also in targeted threat messaging 1 or 2 hours prior to the event occurring. In the case example shown, the mesoanalyst could help forecasters message the potential threats to the Jacksonville metro area well in advance of squall line arrival. You have reached the learning assessment for this module. The assessment is not graded, it's simply provided for your benefit. For each question, you can pause the video if you need to come up with your answer, write it on a piece of paper, then continue the video to reveal the answer on the next slide. Do this for each question in the assessment. Good luck.